Hi everyone, my name is Sankalp Singh and welcome to my presentation for my project on emotion detection from text using LLMs, where I compared full fine-tuning approach with LoRa fine-tuning. This project was conducted as part of CSCI-E 222 course at Harvard Extension School. Let's dive into understanding how these two approaches perform and differ for the task at hand. Before moving further, as we learned in this class about LoRa fine-tuning, LoRa or low rank adaptation is a highly efficient parameter saving technique that freezes pre-trained model weights and only trains small adapter matrices added to specific layers. In contrast, full fine-tuning updates all the parameters within the model, making it much more computationally expensive, memory intensive, and prone to overfitting. Low-rank adaptation injects small trainable low-rank matrices into attention layers while freezing pre-trained weights. We only train two small decomposed matrices within a dimension R, representing rank as a hyperparameter. In this project, I'm drawing comparisons between the two approaches. I added the credits for this image at the end of this presentation. So I use RobotaBase as a pre-fine-tuned model. RobotaBase is a 12-layer, 125 million parameter transformer encoder trained by Facebook using masked language modeling on about 160 GB of text data. The key enhancements over BERT include dynamic masking, a large byte pair encoding over vocabulary of 50K, and large batch sizes, which led to improved performance on NLP tasks. For this project, the training objective is to accurately predict human emotions on Go Emotions dataset. Go Emotions dataset is a collection of 43,000 Reddit comments annotated with about 28 emotion categories by Google Research, like admiration, amusement, etc. The original dataset supported multi-label annotation. To simplify to multi-class classification, I filtered to single label, with about 36,000 examples as training and 4,500 examples as validation and test dataset each. For full-time fine-tuning, I experimented with three learning rates, 1e to the power of -5, 2e to the power of -5, and 5e to the power of -5, with 2e to the power of -5 seemingly performing better. The training was done on Google Colab on T4 GPU. The batch size was 32 for training and a fixed length input as 128 tokens with padding and truncation applied appropriately. I've added more details in the report. The overall fine-tuning took about 40 minutes. I tested on three different learning rates, each taking about 30 minutes. The diagram here shows the chaining validation and training loss. Coming to LoRa fine-tuning, I tried adjusting best rank, learning rate, and dropouts. I tried doing it sequentially. That is first finding the best rank, using the best rank, find the best learning rate, using the best learning rate and rank, find the best dropout on that set with two epochs. And then train using all the three best learning rate, rank, and dropout with 5 epochs. I observed rank 4 underfits. Rank 16 shows diminishing returns with more parameters, but slightly lower F1. LoRa in general requires higher learning rates than full fine-tuning because fewer parameters receive updates. 3e to the power -4 seem to be the best. Also, moderate dropout of 0.1 seem to help regularize adapters without excessively reducing capacity. The diagram here shows the validation and training curve. The final training on 5 epochs took around 50 minutes. I want to highlight that LoRa trained far fewer parameters, that is approximately 900K versus full 125 million compared to full fine-tuning. The accuracy was very similar to fine-tuning though. Here's a confusion matrix for full fine-tuning showing the final results for true versus predicted for top 10 categories. The overall F1 score was around 0.5 and overall accuracy was about 60%, with the best performing classes as gratitude, love, and amusement. The worst performing categories were grief, relief, and pride, possibly due to very few training examples in the dataset. Here is a confusion matrix for LoRa fine-tuning, showing the final results for top 10 categories. Um, F1 for F1 here is around 0.5 and accuracy is 60% again, which is very much comparable to full fine-tuning. Adding some qualitative examples for LoRa fine-tuning here with top predictions. As we can see on a bird's eye view, the emotions predicted are pretty much on the point, specifically for the top categories. Overall, comparing the two approaches, what becomes very evident is that we achieve similar accuracy and F1 scores with almost comparable training time of around 40 to 50 minutes. On the other hand, LoRa needs way less memory and poses much less risk of forgetting base training, considering we are changing all the 125 million parameters in full fine-tuning. It is more adaptable to tasks since we can just switch adapters with base parameters being kept frozen. To summarize, I tried three learning rates for full fine-tuning and found that 2e to the power minus 5 works best, which is typical for models like Roberta. For LoRa, I tested different rank values and found that a rank of 8 gives a good balance. Going higher doesn't help much. Since LoRa only updates a small number of parameters, it needs a higher learning rate, around 3e to the power minus 4, to learn more efficiently. Um, Adding a small dropout of 0.1 also helped prevent overfitting without limiting what adapters could learn. Overall, LoRa proved to be a smart and efficient approach. It achieves similar accuracy to full fine-tuning while training far fewer parameters. And it has the added benefit of being easily swappable for different tasks without retraining the entire model. Possible extensions to this project could include multi-label classification on multi-emotions per text, QLoRa on larger 3B models with quantization, and some cross-domain evaluation on Twitter or customer reviews. Thanks a lot for viewing the presentation. I learned valuable insights via this project that directly helps in my day-to-day work and hope others did as well. Thank you so much.